Good day to our viewers. I am Justin Nashagbulas and I am here to present to you about the application of electrical resistivity, tomography, and geotechnical techniques for identification and characterization of collapsible soils in Bafusam. For our table of contents, we have abstract, introduction, study area, data and methodology, results, discussion, and conclusion. First, let's have the abstract. Road failures have become more frequent to the Bafusam region of western Cameroon, posing serious threats to safety and transportation infrastructure. Collapsible soils that contribute to these disasters are identified by a study that combines geotechnical techniques with electrical resistivity tomography. Subsurface heterogeneity is demonstrated by the results, where different moisture conditions are indicated by resistivity values. The foundation soils are perfect for road collapse and mass movement since they are clay-rich, highly plastic, compressible, weak, and porosity-rich. In order to reduce such failures, the study highlights the necessity of tailoring road descents and construction to regional geological and climatic circumstances. Now for our introduction. Road transit is essential for moving people and commodities in Cameroon. However, many of the country roads, especially those in the west, deteriorate after completion. These failures are caused by a variety of reasons, including human, geological, geomorphological, and climatic influences. The slope and pavement stability are jeopardized by geological variables such as weathered bedrock, clayey soils, steep slopes, inadequate drainage, and heavy rainfall. These problems are made worse by poor construction methods and incomplete site inspection. Areas susceptible to mass migration can be identified with the use of geophysical techniques like electrical resistivity imaging. In order to comprehend foundation soil stability and provide mitigation solutions for the future, this study intends to examine road collapse in Bafusam utilizing ERT and geotechnical testing. In Figure 1, we can see that the location of main road failure sites in the western Cameroon. Now for our study area. This study was carried out at Bafusam, which is in Cameroon's west region, the Bafusam-Bamendu route, and the urban Bafusam neighborhood, were the two failed road segments that were examined, with steep hills and elevation ranging from 1,200 to 1,500 meters. The area has a tropical climate with abundant rainfall from July to October. Geologically, the region is composed of pyroclastic and weathered basalt over a granite-gneiss substrate, producing clay-rich, porous soils that are prone to instability and saturation. We can see in Figure 2 the location of the study area, including the geophysical profiles and geotechnical tests. And to our next slide, the figure shows the rainfall distribution map for Bafusam region, indicating high precipitation levels during the rainy season. It illustrates the study areas receive average annual rainfall of around 1,871 mm, mostly concentrated between July and October. This helps explain the saturation and weakening of foundations soils during these months. Now, next is the data and methodology. This study looked into the reason behind road breakdowns using a combination of geotechnical testing, electrical resistivity tomography, and field observations. In order to evaluate slope profiles and surface features, geological and geomorphological surveys were first carried out. In order to map subsurface structures and pinpoint areas of moisture change, 6 ERT profiles were then obtained. Lastly, the physical and mechanical characteristics of the foundation soils were ascertained using laboratory analysis, hand pits, statistic and dynamic penetration tests, and other geotechnical procedure. In Table 1, we can see that it summarizes technical details of the electrical resistivity tomography surveys, including electrode spacing, profile lengths, configuration, and depths. It shows that both Wenner and Wenner-Schlumberger arrays were used, providing varying sensitivity to vertical and horizontal changes. This setup allows for imaging of subsurface structure to depth up to 38 meters. In Table 2, we can see that it has a list of key inversion parameters used during the processing of the electrical resistivity tomography data. These settings include factors such as the initial and minimum damping factors, robust data and model constraints, and the convergence limit of the root mean square error. These parameters were carefully selected to optimize the balance between model smoothness and data fit. The inversion was performed using the standard Gauss-Newton method, with RMS errors ranging from 5 to 21%, indicating reliable model convergence. Overall, the table provides transparency on how the resistivity models were computed and validated. Now for our results, which is divided into 4. First, we have the field observation of failed roads. We can see in figure 4 that field observation revealed pavements and embankment slope failures at 2 sites. The first site had an 8-meter wide section that northeast to southwest oriented, causing fissures and displacement of road sections. The northwest section failed with the maximum failure located to the west. The foundation soils were clayey, reddish, and containing basalt rock fragments. The secondary road in Site 2 had a 10-meter wide section with larger fissures, with the southern section filling to the northern section remaining in place. The road foundation was built using pavements, body embankments, but drainage and slope stabilization structure were missing. Next, we have geomorphological analysis. In figure 5, shows that the sites have steep slopes and significant elevation differences. Site 1 has northwest to southeast orientation with slopes between 7 to 70 degrees with two slope breaks at 1,326.58 and 1,349.36 meters. Site 2 has a northeast to southwest orientation with slope gradients between 4 to 40 degrees and a slope break at 1,395.15 meters. Next is geophysical characterization of foundation soils. In figure 6, it contains profile which shows 3 main subsurface zones based on resistivity values, which are conductive zone with resistivity values less than 30 ohmmeter, semi-resistive zone with values between 30 to 200 ohmmeter, and resistive zone with values above 200 ohmmeter. The conductive zones C1 appears as a lens structure suggesting localized saturation, contributing to slope instability. The resistive zone, mainly composed of dry lateric gravel or weathered rock, is more prominent at the surface and deeper layers. In figure 7, it shows 3 resistivity zones are identified: conductive zones, semiconductive zones, and resistive zones. The conductive zones is prominent in profile L4 and L5, suggesting widespread water saturation near road failures. Thick saturated layers near surface indicate poor drainage condition and failure-prone sections. Next is the geotechnical properties of foundation soils. In figure 8 shows that the subsurface profile shows clayey silt soils, weathered basalt rocks, and a thin organo-mineral top layer. Penetration test shows soft, heterogeneous materials near the surface, transitioning to more competent layers at different depths. Clay-rich soils and weathered rock fragments suggest low shear strength and high water retention capacity, making the soil profile susceptible to saturation and instability. Table 3 states that the geotechnical analysis of 4 soil samples from Bafu-Sambamen Geote section reveals poor engineering properties in foundation soils. The soils have high porosity, high moisture content, and low dry densities, indicating loose and porous soils. Specific gravity values are consistent and saturation degrees are high, especially during rain seasons. Particle size analysis show a consistent clay content of 60.4% in all samples. The soils are classified as clay, plastic, compressible, and weak, making them highly susceptible to collapse under load and saturation. The soil's friction angles and swelling potential indicate variable cohesion and moderate shear strength. For our figure 9, it presents a Casagrande plasticity chart used to classify the soil samples based on their Atterberg limits. The chart shows that all samples from failed road section are classified as medium to high plastic clays, indicating high potential for volume change when wet, leading to swelling, shrinkage, and loss of shear strength. This high plasticity also affects subgrade stability, a critical factor in road failures, indicating foundation soils are not suitable for road construction with proper stabilization. Now we have our discussion. We can see in figure 10 that it shows the profile at site 1 and site 2. It shows resistive zones with dry lateritic gravel embankment at the surface and wet lateritic gravel embankment at the intermediate zone. A low resistivity zone, a water saturated zone, contributes to slope failure. The upper layer is road embankment material, followed by a dry silty clay zone and a highly conductive water saturated zone. Weathered basalt is observed beneath these layers. The 3D model of figure 11 depicts a layered system with dry lateritic gravel embankment, wet lateritic gravel embankment, and a highly saturated zone. This layer is unstable and contributes to mass movement. At deeper depths, it transitions into weathered basalts. The model highlights the extent and geometry of these layers, confirming the structural and hydrological conditions causing slope instability and road failure. And for our conclusion, this study evaluated the damage to two sections of road collapse by mass movement in West Cameroon using soil testing, electrical resistivity tomography, manual drilling, and laboratory geotechnical tests. Results show that the collapse were caused by seepage water during the rainy season, material nature, and steep slopes of unprotected embankments. The study suggests that pavement design did not consider all natural conditions, and safety pavement platforms must be built for rehabilitated to support future road mass movements. Proposed solutions include surface pavements, construction infill and excavation zones, and stabilization of sub-base layers. And that's all for my presentation. Thank you for listening to my presentation, which is named Application of Electrical Resistivity Tomography and Geotechnical Techniques for Identification and Characterization of Collapsible Soils in Bafoussam, which is located in Western Cameroon.